Okay, and so the next speaker is Michael Aizenman, who'll be talking, as you see, on the decay of correlations under quenched disorder.
I would like to start by thanking the organizers for the invitation to this excellent workshop. Both personally and professionally as a mathematical physicist, I enjoy being at a place where different cultures meet. And I enjoyed hearing these themes in the introductory comments yesterday, both by Professor K.K. Foy about the mission, his view of the mission of the center, and by Professor Englert, who described the spirit guiding his work with Robert Brout. Now, given the importance of symmetry breaking and the focus on that for Robert Brout and the conference, I thought of talking about a phenomenon which is related to the effect of disorder on continuous symmetry, or on symmetry breaking, discrete and continuous, the so-called Imrima effect, and questions related to that. So this is a subject which in the past has attracted a great deal of attention, discussion. The big dispute was settled, but actually more recently a next order question arose, so it was brought to the fore, and I had some ongoing work on that with Ron Peled from Tel Aviv University, which I would like to talk about here. For some reason, this does not seem to work. Is there some sort of remedy to that, perhaps? Sorry? Perhaps it's the other one. This does not seem to advance the slides. There may be an on-off button. Thank you. Okay, so it's a bit lengthy, but let me just flash here the abstract as it was presented originally. My thoughts on the subject actually have evolved since then, but let me just quickly go over that. Sorry. So the basic phenomenon is that in sufficiently low dimensions, the addition of quenched disorder to a translation invariant Hamiltonian may result in the elimination of symmetry breaking. This phenomenon, the Imrima phenomenon, is exemplified by the two-dimensional random field Ising model, which I would present here. For continuous symmetry breaking, such as ON models, the roughening effect, the elimination of discontinuity, actually persists up to including 4 dimensions. So the talk will focus on the question of possible existence at the critical dimensions of d equal 4 for continuous symmetry breaking and 2 discrete, of another transition which is reached by varying the strength of the disorder. The result, if it occurs, would be a Kosterlitz-Taules type phase transition, which is nowadays is not really expected, but the issue is still open in 4 dimensions. I'll try to explain all these words as we go along. The talk is based on a joint work with Ron Peled at Tel Aviv University, and my collaborators on past works on the subject include Jan Wöhr, Joel Leibowitz, and Raphael Greenblatt, with whom we worked on the quantum version of this phenomenon. So let me start by introducing it in the simplest case. The simplest example we have of symmetry breaking is the Ising model. It's the system of variables. Sorry, it is described by a collection of binary variables, sigma v associated with sites on a graph, say the three-dimensional lattice ZV. The energy function is written here. It's just sum over neighbors of product of the spin variables, minus j, and j in this discussion is a positive constant. So the energy is minimized in 2 configurations, spins all up or spins all down. And there's of course two global ground states. The symmetry is removed by the addition of an external field, which is this term sum over sides of H times sigma V. For H positive, the ground state is where all spins are up. H negative, the ground state is where they are all down. Now, the disorder may be added to the system by replacing, or if you wish, adding to the external field, which is random terms representing noise, but they represent quenched disorder. So the discussion would focus on what happens if you have terms which are generated as, say, independent, identically distributed variables, and the nature of the distribution is not so important, although it's preferable to have them continuously distributed. So it could be Gaussian or just uniformly varying between plus minus 1. And then there is a parameter epsilon in front with which we control the strength of the disorder. And of course, the most interesting cases occur when H is equal to 0, when without the disorder, there is a degeneracy in the ground state. Now, whatever is said about the Ising model, whatever I said so far about the Ising model, generalizes to systems with continuous symmetry, such as the ON models, for which you just replace the spins by vectors. So this would be, say, in the ON model, this would be n-component unit vectors at each side, kind of little magnets, if you wish. The external field H would also be then given by a vector. These are your control parameters. We would be interested in the case when H is 0, but the disorder would also be given by randomly oriented, say, unit vectors or Gaussian vectors with coefficient epsilon controlling the strength of that. Now, the general theme of the effect of the Imriman phenomenon is, well, it's slightly more general. One way to think about what we are discussing is you start from a translation invariant system, and you then add disorder to one of the parameters. And the general phenomenon I've described applies regardless of which parameter you disordered or you randomized. So an example of such a situation with a different parameter would be, say, the Q-state Potts model. Q-state Potts models are obtained by replacing the binary spin variable by a variable with Q values. Sigma V now takes, instead of 2 values, Q distinct values. This is of interest because for Q large enough in 2 dimensions, the phase transition, and in a minute I would show the phase diagram, actually shows a first order transition at the critical point where the spontaneous or residual magnetization actually jumps from 0 to a positive value. In that case, randomizing the coefficient J would again result in low dimensions in the rounding of that transition. And as before, eta would be, for example, uniformly distributed between -1 plus 1. In this case, that's a bit simpler to consider than the Gaussian case because, well, so actually, it doesn't really matter. Well, what I wanted to say is that in case eta is large, you run into another issue, which is then the model becomes not ferromagnetic, and then there is room for frustration. But this actually does not play a role in what I'm discussing. And as before, whenever you have symmetry, it's natural to consider the effects of a additional parameter which removes the symmetry from the Hamiltonian. And in this case, we would be talking about the equilibrium state, which is obtained by removing H to 0. So here is the phase diagram of what I discussed before. if you take the Ising model, the phase diagram is described in this plane of temperature and external field H. And as is generally known, the equilibrium state is actually analytic in HT, except along the line of zero magnetic field, the Imry-Ma phenomenon, the Li-Yang phenomenon. Along the line H equals 0, there is a first order transition across a line from the critical temperature down to 0. So if you look at, say, the magnetization, which is defined down here, for general field and temperature, the magnetization is just the expected value of the spin variable at the selected site. The limiting value of that, when H is taken to 0, as here, that's the residual or the spontaneous magnetization. And the limit is non-zero along a line, along a line where the limit depends on the direction that this line was approached. For Q-state Potts models, this diagram should not be confused with this. Here I'm plotting the function, the spontaneous magnetization as function of the temperature. So this is a different plane than the picture above. And for Q-state Potts models in 2 dimensions, Q greater than 4, the spontaneous magnetization starts with a jump, unlike the Ising system. And again, the claim is that, the theorem is that in low dimensions, when you randomize the parameter which drives this transition, so in this case it was J, this jump discontinuity would be rounded off. The discontinuity is eliminated, corresponding to the statement that at the critical point you do not have coexistence of distinct phases with different values of this parameter. So the initial questions which were debated concern first the conditions under which the first order transition persists under quench disorder. And then one can go beyond this into questions of how does the addition of random terms affect the critical exponents, critical behavior, and so on. Now, there's an amusing history to that. It started in an article, actually we already heard a bit about this system yesterday in the talk by Edouard Brezin, although there was minor corrections. I'd like to make a minor correction to that. The first work that I'm aware of on that was the Imry-Ma paper, which was written in 1975. And they presented essentially very robust arguments, which were outlined in the talk of Professor Brezin yesterday. For scaling reasons, which he outlined, and I would go over again, one is led to the conclusion that the discontinuity would persist if the dimension is greater than 2 in case of Ising systems and more general situation that I described before. And furthermore, the discontinuity, or if you wish, the discontinuity would be rounded off in 2 dimensions and below in the discrete case, and it will be rounded off in 4 dimensions and below in case of continuous symmetry. The argument is quite convincing, and when it appeared, my understanding is that it was met with approval and acceptance, except that short time after that, other more sophisticated arguments were developed based on field theoretic analysis of the critical behavior in a series of papers, including Grinstein, Aharoni, Imry-Ma, the authors of this, and Parisian Surlas gave it an extra oomph. And by more sophisticated field theoretic arguments, the conclusion which was reached is that the general principle of dimensional reduction applies here, which is that the critical behavior of a system with disorder, as was described over there, in d dimensions is similar to that of a homogeneous system in d minus 2 dimensions. That actually at one point, in case of Ising model in 3 dimensions, for example, these two principles actually lead to different conclusions. And then there was a very lively debate of which do you believe is correct. There was a period when I remember at meetings which were and continue to be run by Joel Leibovitz. At the time, Joel would ask the audience to take an opinion poll, and the opinions were quite divided. And eventually, the consensus has settled, in fact, in this case, with the help of rigorous results, which I will mention shortly. But one interesting aspect of this debate was that whereas the original argument was quite convincing, the second argument also made a lot of sense for people who are well-versed in field theoretic methods, in statistical mechanics. When you have to choose between them, and the choice was hard, I think it became clear that we do not fully understand either of these. I mean, when you have to vote between two reasonable choices, you start to appreciate that we do not have full understanding of what seemed to be a very natural argument. So before describing the results, I would like to make a comment about the thermodynamic formulation of these questions. So as you know, we heard about the concepts of statistical physics. We had a crash course yesterday or two. But the first accomplishment of statistical mechanics was to actually provide an answer to the question of where is thermodynamics coming from. The thermodynamic description of phenomena that we are talking about is coarser. It relies on analysis of fewer quantities, such as the bulk free energy density, its dependence on the temperature, or beta is inverse temperature, or the parameters like the magnetic field. And the questions which I'm describing can be discussed both at the level of thermodynamics, where the issue is, if you go up here, whether there is a discontinuity in the expected value of the spin, or coexistence of different Gibbs states, Gibbs equilibrium states, at a point where the two limits are different. That's a statistic mechanical version of the problem. But you can also raise it up level to the level of thermodynamics, and you gain a certain simplicity of formulation. Let me mention this before I go through the analysis of that. Actually, it was useful for us to lift the proofs to the level of thermodynamic arguments rather than statistical mechanical one, because when it comes to quantum systems, the manipulation of Gibbs states becomes trickier, since we are dealing with Gibbs states of systems with non-commuting variables. However, when you lift it up to thermodynamic level, the classical arguments actually generalized easier, and the result which I am talking about, in fact, was shown to apply also, to hold also for quantum systems. So here is the quick summary on this transparency of what's the thermodynamic manifestation of what we are discussing. So first of all, the free energy in statistical mechanics is usually defined as the log of the partition function, which is just I did not write it here, I think. Did I? No. But let me assume that we know what partition function is. It's just sum over all the configurations in a finite volume of the Gibbs factor e to the minus beta h. The log of this serves as a generating function. So take the log of that, divide by the volume. More precisely, what you get out of this is the free energy, because, again, it was discussed yesterday, so let me fall back on that. The partition function includes the factor e to the minus beta h, which gives you e to the minus beta energy times the entropy, e to the entropy. So when you take the log, divide by the volume, and minus beta, you are left with the free energy of the system. So there is a basic result. The first step in statistical mechanics is the result that for homogeneous systems, the free energy per unit volume actually exists. The limit exists if you take sequence of regions, regular regions, say Van Hoek limit. That property persists, so this basic fact persists also in the presence of disorder. All you need is to know that the disorder which was added to the Hamiltonian is given by an ergodic process. So for example, system of independent identity distributed variables certainly meet this criteria. So the free energy exists, and its value is independent of the disorder and of the boundary conditions. So that's a fairly easy statement to prove, although it took initially a while for some to recognize that. As we know, the derivatives of the free energy with respect to the parameters that it depends on actually provide you with the values of the densities of conjugate variables. So when you differentiate the free energy with respect to H, again, it's a general statement that for any large statistical mechanical system, the derivative of the free energy with respect to H is equal to the infinite volume limit of the volume average of the conjugate variable. In case H is an external field coupled to spins, this will be the magnetization. The free energy, I skipped a line here, by general principles, the free energy is always concave as a function of each of the parameters which appear linearly in the Hamiltonian, like the magnetic field. And the uniqueness of the limit does not, well, tells you that you always have the free energy which is a concave function, say of H or other parameters. The function does not depend on the boundary conditions. However, when it comes to derivative, the function does not absolutely have to be differentiable. It almost has this property because concave functions are differentiable at all points except possibly a countable collection of sites, but these are the points where phase non-uniqueness may happen. So, however, by general principle, you know that at any temperature and any point in the phase diagram, temperature and magnetic field, at which this concave functions is actually differentiable, which means that the left and right derivatives agree. At any such point, the bulk average of the conjugate quantity exists and coincides for all Gibbs states, even if there is more than one Gibbs state at that point, this point. So they are given by the thermodynamic functions. Therefore, the question of whether there is a discontinuity in the magnetization or not can be thrown onto the question of whether the limiting free energy is differentiable with respect to the magnetic field or not. In the presence of symmetry breaking, like in case of Ising model, the free energy as function of H has a kink discontinuity at the origin. The derivatives are giving, the two derivatives are not equal. They give the plus and minus spontaneous magnetization corresponding to the two different states. So the Imrima phenomenon is that in low dimensions, the free energy which is obtained by adding any amount of disorder, it becomes differentiable. The kink discontinuity which we had would be rounded off. So let me now quickly mention some of the rigorous results which settle this very interesting and raging discussion in the 80s. So first is the result of John Imbri for zero temperature and Jean Bricmont and Antti Kupiainen for positive temperatures. What they proved is that in 3 dimensions, at sufficiently small disorder, the random field Ising model continues to have a first-order transition in the magnetic field, both at zero temperature and at small enough temperatures. as you know, one of the basic issues in the phenomenon which we are studying in statistical mechanics normally is the effect of fluctuations which are thermal nature, so thermal fluctuations. Here, when in the presence of disorder, you have fluctuations which are due to the frozen disorder. And in that case, what is found is that often the question which exists at zero, the question of interest about the effects of disorder is encountered already at zero temperature. And issues related to the effect of disorder are often non-trivial already at the ground state, trying to understand the nature of the ground state or ground states. So this theorem says that in 3 dimensions, when you, and 3 and higher dimensions, when you take an Ising model with random field, let me go back to the Hamiltonian, in the presence of the disorder, this system would have a unique, would have more than one ground state in the infinite volume limit, and these ground states actually express the fact that if you take sequence of large volumes, changing the boundary conditions out there, actually the change propagates into the system, throughout the system, and as a result, you have more than one ground states, even in the limit in which the boundary was taken out to infinity.
Is B equals 2?
The boundary effect persists if D is greater than 2. In 2 dimensions, the opposite is true. And that's the Imriman phenomenon that I wanted to say. Thank you.
It just doesn't say it.
Sorry?
Same slide.
Let's see. D equal 3. In 3 dimensions, it's sufficiently small disorder. The random field continues to have, Ising model continues to have a first order phase transition, meaning that it has more than one ground state. Ising model is further simplified in this case by the fact that you have correlation inequalities, due to which the ground states of the system actually are ordered. There is the one which is more, which has, there is a partial order on the collection of ground states of this system, which reflects the fact that as you raise spins at the boundary, the corresponding ground states, which are unique for each boundary configuration, also go up. That's an expression of the ferromagnetism of the model. So the crux of the matter is the question of whether the ground state that you obtain with plus boundary conditions fixed very far differs from the ground state with minus boundary conditions. Anything else, any other boundary conditions would be sandwiched between these two. So quite generally, either the plus and minus boundary conditions disagree, lead to different states, or else the boundary conditions are irrelevant. Why should they be irrelevant potentially? Well, because to minimize the energy, the spins should optimally agree with both the field at the side and with the neighbors. Of course, there's no way that the spin can simultaneously, that all spins can be lined up with the fields which are disordered and with neighbors. But what you may expect is that at small epsilon, there will be predominantly agreement, but in each, up to a certain scale, the agreement, the spins would agree on a value which would be either plus predominantly or minus, depending on the local average of this random field. So the question is, what is stronger in the presence of disorder? Is it the pull of the boundaries, which can be manipulated by us? So actually we have the two extremal cases, plus and minus, or the random field, which freezes in the disorder. And the statement is that in 3 and more dimensions, the boundary conditions actually win, whereas in 2 dimensions, that's the joint result we had with Jan Ver, in 2 dimensions, at any level of disorder, there almost surely is a unique ground state. This sort of results persists also for continuous symmetry breaking, but in this case, it's even more exciting. You can show that the randomness actually results in a unique, the frozen disorder results in there being a unique ground state, almost surely, up to 4 dimensions. 10 minutes, thank you. And as I said, this applies also to quantum systems. Just to give an idea of how does one prove such a result, what we looked at is this quantity G, which is defined here. It expresses the difference in the contribution of the disorder to the ground state between the plus and minus boundary conditions. So there are 4 terms here. One is the minimal energy for a system with plus boundary conditions and the disorder frozen in, minus the ground state with a minus boundary condition. But I would like to identify here just the term, the contribution to this difference due to the disorder in a smaller region, say at the core of this domain. So we subtract from this the corresponding difference for a system where for which the disorder was set to 0 in this region. So in the limit when n tends to infinity, these are very large. In fact, the outer boundary can even go faster. These are 4 very large quantities, but the difference between them is uniformly bounded by just the size of the boundary of the smaller region up to constants. And the reason is that if you remove from the Hamiltonian the couplings across this boundary, you affect each of these 4 terms, which in principle can be much larger. You affect it at most by the boundary of the inner core. And once you remove those couplings, the minimization that you perform here can be done completely independently, and this quantity ends up to 0, being equal to 0. The other interesting property of this quantity G is that its derivative with respect to the applied field at site X is just the difference in the magnetizations between plus and minus boundary conditions. So we have a quantity here which on one hand is bounded by the surface, L to the d minus 1. On the other hand, it depends on a bulk collection of variables. And if there is a difference between the plus and minus boundary conditions, there is a true dependence on those. So you can actually turn this into a proof that assuming that the probability of the ground states to be different is non-zero, assuming that there's a difference between the plus and minus spontaneous magnetizations. If that is true, then this quantity G, by virtue of its dependence on all the bulk collection of terms, should be at least of the order of square root of the volume. In fact, it should be Gaussian on that scale. So now the question is, you have a collection, you have a variable which may be of the order of square root of the volume times normal variable, yet it has to be bounded by the size of the surface. So you do a quick calculation, and you see that in dimensions in which d minus 1 is, in which d over 2 is greater than d minus 1, the fluctuations would be inconsistent with that bound. Okay, that's at the critical point. This argument also extends, because then the inconsistency is derived between the fact that the quantity on one hand is bounded by constant times L, and yet it has normal fluctuations on that scale. And as was mentioned yesterday, that can be extended to continuous symmetry breaking, where the effect of disconnecting from the outer boundary is not surface, but L to the power d minus 2, due to the possibility of soft rotation away from the boundary. Now, this brings us to the next question, which is, what can be said about what can be said about the decay rate? So now we have, okay, now I would like to come now to the question which is currently debated, or was discussed then, but it's still partly open. You have a situation in low dimensions that the disorder determines a unique ground state and a unique Gibbs state. So in principle, the zero temperature magnetization is just function of the environment, the frozen environment. To what extent does it depend then on the environment at distance L? You can easily show that at high disorder, the dependence decays exponentially fast. The spins would be determined by the mean magnetization near to a given site. However, at weak disorder, this is far from clear. And even a heuristic analysis suggests that if there is an exponential decay, the decay is at extremely low rate, as e to the minus constant over epsilon squared. A possibility which is discussed, and that's the last transparency, is that at weak enough disorder, there may be a transition where in the low temperature phase, there may actually be only a power law decay. And there's a beautiful picture which goes along with that, which is potentially misleading. I now believe that, I skipped here the result which we had. There was recently an article posted in which it was shown that the magnetization in the presence of disorder, the critical dimension, decays as 1 over log L. This is a very weak bound. With Ron Pellet, we have a preliminary result that it decays at least by a power law, but I believe now that that the argument extends to a proof of exponential decay for Ising model at any level of disorder. The question is, however, even more open for continuous symmetry breaking. And there I want to say that if at 4 dimensions you would have a phase transition as function of the disorder, that actually would be a very gratifying reemergence of the dimensional reduction principle, because according to that, the critical behavior in a system in the presence of quenched disorder in d dimensions resembles that of homogeneous in d minus 2. 4 minus 2 is 2 dimensions where you have the Kosterlitz-Tauris transition. So it would be quite interesting if you could have that sort of a behavior for the Ising system. Just to explain this picture, if you're asking at low disorder, what is the value of the ground state at a given site? A sensible algorithm seems to be calculate the average of the magnetic field in a region of size R. Things are balanced, as we saw before, and the probability that this Gaussian variable of order L actually overwhelms the boundary pool at low disorder, this probability is very small, e to the minus constant over epsilon squared, because it's the probability that the Gaussian variable times epsilon overwhelms a constant. This is very small. However, it's scale independent. So if you try first scale, most likely you would find that the field is still not sufficient to dictate the value of the spin in the region, ignoring the boundary. But keep trying. Eventually, and it may take many scales, eventually you would reach a scale where the average actually overwhelms the boundary, and that's a sensible guess that this may be the local magnetization. So if you ask how, in a finite region, what determines the spin configurations, this suggests that for each region you should do this sort of calculation and wait until you reach the scale at which things are decided. That brings to mind 2 interesting stochastic geometric models. One is the Swiss cheese, the scale invariant Swiss cheese model, and related to it is Mandelbrot's canonical curdling, which is just kind of a block hierarchical reorganization of that. The Swiss cheese model, let me talk about this because time is running up. The Swiss cheese model is obtained by thinking about a Poisson distribution of spheres. In d dimensions, this would be balls of radius r, and you take the only distribution which is translation invariant and scale invariant. up to a cutoff on the radius. And about that, you can prove that if you pick a priori a point and ask what is the probability that this point is still not covered up to scale r, that actually decays to 0. In fact, you can even take the continuum limit in which we keep the outer box. We look at the model at the scale of the bulk, but take the lattice spacing to 0, and then you have a continuum model described here. You can show that because of the scale invariance, the probability of a point not being covered is 0, but that does not mean that nothing is left. In fact, when you remove such balls by this process, when lambda is small enough, the stuff would be left behind. What you can conclude is that the Lebesgue measure of this region which is left behind is 0. However, for small lambda, the set is non-empty. Its Hausdorff dimension increases as lambda goes to 0. And actually, at low lambda, it even includes some percolating regions through which influence may propagate. The last comment is that this, the last comment is that this sort of process actually, the properties of this Swiss cheese, scale invariant Swiss cheese, were noted in relation to post-Big Bang exponential inflation process. Years ago, there was a talk, there was an active discussion of the cosmic inflation. Alan Guth was pointing out that in the inflation process, about which we heard in the first lecture here, because it's also part of the Brout angular picture, the universe was born in a different phase that is stable now. And during the inflation, it actually underwent phase transitions, which were started by nucleation events. And due to the exponential rate of the inflation, the picture today, which is consistent with that, is that the universe would be also marked by a set of this sort of domains, which essentially exhaust all the volume. However, the mathematics tells you that if lambda is, if this density is with small enough parameter, there will be some primordial stuff left there in the form of zero measure in this limiting situation set, but set which actually may include even complete surfaces. So I just wanted to mention this process, and somehow it reappeared in the relation to a possible behavior of this random field problems. As I said, I believe that for Ising model, the picture which this suggests is wrong, that there is eventually a cutoff and you have exponential decay of correlations, this picture notwithstanding. The question is much less clear in case of continuous symmetry breaking. Thank you.
Questions? Yes?
Yes. Okay, thank you very much. What I can say from, I think everybody knows that dimensionality tends to bring order.
Tends to be?
Order. Because when you introduce this order then it can only get order if the dimensional is higher. Two-dimensional Ising models get order in 2 dimension, right? And then if you introduce this order interactions, then what you saw in your presentation is that the dimensionality, lower dimensionality is 4, something like that. And the question is, actually I would like to, your comment about there is, we know that Potts model is a second order for Q
Less than 4.
Less than 4.
Yes.
And there is maybe something like introducing the virtual or extra invisible state to the key Potts model can transform the second order into first order.
Yes.
But this invisible states, it doesn't directly contribute to the energy.
I'm not sure I follow. There are two different questions. One is, what is the ground state energy? Okay, it of course is affected by this order. The other is whether the ground state is unique or the extent to which it is not. And can you produce two ground states which are macroscopically different, maybe not just a single domain wall like an Ising model which is plus half and minus half, but can there be two ground states which extensively look different and yet minimize the energy, each one with appropriate boundary conditions? And the basic phenomenon is that in high dimensions, the effect of the boundary conditions percolates into the system. You can talk about influence percolation, and it percolates in high dimensions.
And this brings order, tend to brings order, right?
It's the analog
Because
of the symmetry breaking which you have in the homogeneous case. Symmetry breaking is the phenomenon by which the ground state actually is not unique, and like piece of a magnet remembers, I mean, can be magnetized in more than one way, in fact a continuum of ways, which remembers, so to say, either the external field which existed when it was cooled off and removed, or else it can be manufactured by presenting just boundary conditions if you have enough patience for this effect to percolate. That persists in high dimensions but not in low dimensions. And low means even up to 4 in case of continuous symmetry. You asked about critical behavior.
Yes.
The upper critical dimension for, say, Ising models is 4. Above 4 dimensions, the critical exponent no longer depends on the dimension. According to the other side of the story, which I will not discuss here, that upper critical dimension is moved up by 2, quite generally. That's the other set of predictions.
Okay, thank you.
Okay, any other question? But then let's, yes, there.
Hi, is this kind of phase transition similar to the dynamical quantum phase transition?
To the
Dynamical quantum phase transition.
dynamical phase
Yes.
transition.
Dynamical quantum phase transition.
Oh, dynamical quantum phase transition. Yes. There is a, I'm not sure I fully understand the question, but you can think of the quantum spin chain with transverse field and equilibrium statistical physics of quantum systems can often be viewed as sort of a dynamical system in which you have imaginary extra dimension. And in that case, the phenomenon that I'm describing does go through. So in other words, quantum spin chains in one dimension resemble statistical physics of 2 dimensions. So what was said, I'm not sure I'm answering your question, but the mathematical argument which exists here for the Imry-Mach phenomenon for classical systems yields analogous result for one-dimensional Ising models with transverse magnetic field, once you introduce some randomness to that.
Thank you.
Okay, any other question? But then let's thank the speaker.